Hello and welcome to Vector Calculus with Sal. If someone asks, how fast is the air going around an airplane wing? Well, the answer is it depends. Are you talking about a point above the wing or perhaps below the wing where the speed of the air might be lower and its direction is different? Or maybe even farther down along the wing where the direction and speed is also different. What we're getting from all of this is that it depends on which point you're talking about. And depending on that point, you want to know the actual speed of the air, but you also don't want to know what direction it's going in. So you would like the velocity, and velocity is a vector. At the end, we need a tool for describing something that once we give it a point, it gives us back a vector. What we need are vector fields. A vector field is a function from point space to vector space. Here we represent our point space with the point xy written in blue, and the point xy gets mapped to the vector written in green, where its x component is a function of two variables called f, and its y component is also a function of two variables called g. Notice that both f and g are functions of the point written in blue, xy. Now this could be a little confusing and it takes some time to get used to it. You have to separate in your head between the point xy and the vector with x component f, the function f, that depends on both the x value of the point and the y value of the point, and the y component of the vector, which depends on both the x value of the point and the y value of the point. It takes getting used to, and everyone still messes up when they draw vector fields, so don't feel bad about it. What I found to be helpful is to just not think about it too hard. Take my x value in the point and just plug it into the vector. Wherever I see an x, I just replace that with the number that's the x value of the point. Likewise, do the same thing with y. Wherever you see y in the expression of the vector, replace it with the y value given in the point. It takes getting used to, and it's worth repeating, that the x component of the vector, f, depends both on the x value of the point and the y value of the point. Likewise, so does the y component of the vector, g. So let's take a specific example of a vector field. Here you have the vector field that's called the rotation field, and hopefully you'll know why it's called the rotation field by the end of this video. Notice here that the x component of our vector field is equal to minus y. Now what does that mean? Again, that means that our function f, which is a function of two variables, x, y, is equal to minus y. Likewise, our y component of the vector field is equal to x. Which x? The x value of the point that we plug in. Of course, this is all counterintuitive. Our x component of the vector depends solely on the y value of the point, whereas the y component of the vector depends solely on the x value of the point. Now, of course, this is true just in our specific example, and it does twist your mind a bit, but don't forget, the vector field that we have in our example is called the rotational field for a reason. Now, let's give our rotation vector field a specific point. Let's give it the point 2, 1 written in blue there, which has an x value of 2 and a y value of 1. Now, on the right, I'll start writing out my vector. Notice here that I'll leave a parenthesis in the x component. Why? Because there was a y over there. And what am I going to plug where I saw a y over there? The y value of my point. Let's now start filling out the y component. Again, I leave a parenthesis. There was an x over there. And what am I going to fill that x location with? I'm going to fill it with the x value of my point, which is 2. So what does this vector field give us back when we give it the point 2, 1? It gives us back the vector with x component minus 1 and y component 2. Alright, so now we know how to get a vector once we give the vector field a point. Now we're left with the task. How can we visually represent the vector field? We've visually represented many other mathematical objects, the simple function of one variable with an xy plot, even functions of two variables using a three-dimensional graph. So take a moment to think about this design problem, if you will. How can you visually represent a vector field? I hope you took a moment to pause the video and think about this problem of how to visually represent the vector field. Well, here's an idea. Why don't we begin with our point space? Now, our point space will be represented in blue, and what you're seeing here is the x and y axes of our point space. Now, let's go to the point 2, 1, which is the point that we gave our vector field, our rotation vector field, in the example that we've considered. Our vector field then returned back the vector -1, 2, which you see here written in green. So what are we going to do with this vector -1, 2? Well, here's an idea. In green, I'm going to draw the axes for our vector space. I'm going to place the origin of our vector space axes right at the point 2, 1. And now, in green, I'm going to draw a vector just like I would with any vector coming out of the origin. It has an x component -1 and a y component 2. Notice the trick here. We're overlaying our vector space axes above our point space, making sure to place the origin of our vector space at the point where we wish to plot the vector for our given point. Here, we're plotting our vector for the point 2, 1, so we place the origin of our vector space at the point 2, 1. What we could do now is zoom out and repeat this process for as many points as we have the patience to do. So we can continue to draw vectors at any point where we wish to represent what that vector field would return if we gave it that point. Drawing axes for every single vector that we want to represent will get too cumbersome. So we'll just draw the vector without overlaying the axes. Of course, in each of these vectors that we draw, it's implicit that we have axes and the origin of those axes is located at the point in the blue space which we wish to attach its respective vector to. So let's start plotting our rotation vector field from scratch. We'll do so drawing typical axes, which of course after this video we know is actually the point space axes, and we'll go to each point which we wish to attach a vector to. We'll attach at each point the vector that we would get if we gave our vector field that corresponding point. Doing so for as many points as we have the patience to, and hopefully enough to get a sense of how this vector field would look, so we can continue this process, draw out as many vectors, and hopefully now you see why it's called the rotation vector field. It'll play a prominent role when we discuss Stokes' theorems and all of the exciting stuff that are found in vector calculus.